Good morning, Algebra 2 students. Today we're going to finish up lesson 6.7. Remember we just talked about on Friday finding the possible number of positive reals, negative reals, and imaginaries. And you were to do problems 7, 8, 9, and 10 on the 6-7 practice. Now, today we learned about something called the complex conjugates theorem, which says that if A plus BI is a 0, then A minus BI is also. And those are considered conjugates. So for example, if 2 plus I is a root, then 2 minus I must also be. If 3I is a root, negative 3I must also be a root or a 0. Therefore, the imaginary zeros will come or must come in pairs, and there must be an even number of imaginaries. So if you look at those tables that you did for Friday, I think you will see that your column under the imaginaries will all be zero numbers, or even numbers, sorry. All right, so a couple examples we're going to do today. Today we're just going to, if I give you a polynomial and ask you to find all the zeros, we're going to use all the techniques that we have learned, which is factoring. And for this first example that we're going to do, I would look at this, I would check and see if there's a greatest common factor, which there isn't, and then I believe there are 4 terms. So I would try to do this by grouping. So these first 2 terms, I'd take an x squared out, which would leave me with x plus 1. And therefore, if I can do it by grouping, this needs to be x plus 1, which means I'm taking out a 9. Therefore, it would factor to be x plus 1 times x squared plus 9. X squared plus 9 does not factor because it's sum of squares. My solutions, or my zeros, would be negative 1, and then whatever makes x squared plus 9 equals 0. But if I solve this, I would subtract 9. I'd take the square root of this, positive and negative, and that is positive and negative 3i. So you can see that those imaginaries did come in pairs. We did have the conjugates of those. These are taken from the 6.7 practice. This first one is just a linear equation, meaning it's first degree. I would simply just solve for x. So it'd be negative 15 ninths, and then it would reduce. If I take a 3 out of each of those, it'd be negative 5/3. So I've got 1, 0, and it is a negative real 0. Number 3, using my factoring techniques, I could take an x out, which would leave me with x to the 4th minus 81. And then I realize that this is difference of squares. So I'd have x squared minus 9 and x squared plus 9. And then the x squared minus 9 is also difference of squares. And the x squared plus 9, I realize I cannot factor that. So once again, my solutions would be 0 because of the x, positive 3, negative 3, and whatever makes x squared plus 9 equals 0, which again, if I solve this, I would subtract the 9. I get a positive and negative square root of a negative 9, which is a positive and negative 3i. And those would be my 5 zeros because it was 5th degree. You can see I did have 2 imaginaries in this case. Number 5 on the practice. Pay careful attention to this one. So number 5, I think if you go through all your factoring techniques, there's not much you can do. There is no greatest common factor. It's not one of the special ones. We could not do grouping, and it is not in quadratic form. So not a whole lot I can do. But I did remember, or we did just talk about that the number of positive reals for this one would be 0 because there's no sign changes. The number of negative reals, again, if I would change the odd powered terms here, then there would be 1 negative real because there's 1 sign change. So this is the only possibility for this. So I need to find out what that 1 negative real is. To do that, I'm just going to do a little bit of trial and error. I'm going to try -1, and I'm going to do this synthetically. So I kind of just go on a little search party trying to find what would work here, and this does not look like it's going to work. So then I might try -2. And do this synthetically. And this is working. So I do know that -2 is a 0 of this function. And I'm left with this quadratic, x squared minus 2x plus 10. Now, we've learned how to solve those quadratics. This one here, I don't believe it would factor. So I would use the quadratic formula. If I do my discriminant, I would do 4 minus 4 times 1 times 10. 4 minus 40 is a -36 over 2a. So it's 2 plus or minus 6i all over 2, which would be 1 plus or minus 3i. So for number 5 here, we did this kind of by trial and error. We had to find 1 negative real that worked, which we did. And then we got these 2 conjugates as our 3 zeros. I'm going to come back with another video that's going to talk about writing polynomial functions given the zeros